When you design your filtering algorithm for a constraint, you should ask yourself if it's interesting or not to call the same filtering a second time consecutively. And the property that makes this useless is called idempotency. A filtering algorithm is called idempotent if executing it twice in a row always leads exactly to the same domains. And so just one execution is enough. And so you can spare at least one execution in that case. So let's consider the sum constraint. That is the subject of our study for idempotency. So we will say that the sum bound consistent filtering algorithm is idempotent if you call the same filtering on the result of a first filtering there is the same as the result after the first filtering. Okay, D prime is the result after the first filtering. So if you get exactly the same domains a second time as after the first time, then you say that the constraint is the filtering algorithm is idempotent. And so why do we care? Simply because we avoid scheduling a second time the constraint in the fixed point algorithm. So is it the case for the sum constraint? So I can already tell you that it's the case. It's the case at least if you have interval domains, as it's the case in that in the example with 3 variables. Okay. If it's the case, you can convince yourself that if you update one maximum and one minimum value, it means that the other extreme value, the other minimum or maximum of the other domains participate in a solution. And we will call that a support. And clearly, a filtering algorithm will never remove a solution, so it will never remove a support. And so it will not be able to update further the maximum and the minimum of the other variables. So assume, for instance, that we have, as we did before, we have updated here the maximum and the minimum of this variable x1. So if we are able to update the maximum of the variable x1 to 24, it's because we use 4 and 20 as a support. And so together, minus 24 plus 4 plus 20 is equal to 0. So you see that the support of that maximum value of x1 domain is the minimum of the other domains, of the other two domains. Okay. And so because we were able to update it to minus 24, you know that we will not be able to shrink further the minimum of the other domains because they participate in a solution. And for the same reason, we were able to update the minimum of the domain of x1, and so therefore, these two values also participate in the solution. Minus 66 plus 6 plus 60 equals 0. And so that's the reason why calling the bound consistent filtering for the sum constraint a second time is not interesting if you have interval domains. Let's now consider the situation in which we don't have an interval domain for the variable x1. Instead, we have a set of values. We have 4 values, minus 100, minus 25, minus 24, and 10 for x1. So the update will be the same as before. We will constrain x1 to be within the interval minus 26, minus 24. But if we do that, it means that these two values will disappear from the domain. So minus 100 and 10 will be removed from the domain. The consequence of that is that by applying again the same bound consistent filtering, we will discover additional filtering on x2 and x3 now. And it means that the sum constraint is not idempotent. It's not idempotent because we have holes here, we have gaps in the domains of x1. And so when you have gaps in the domains, you should always call the same filtering for the sum constraint a second time, the same bound consistent filtering a second time. You might discover additional filtering in that case.